We're going to look at z-scores next, and this might be probably the first real abstract idea that we've come across, I'm guessing, as far as you're concerned. Now, the concept of standardizing data is very common. What this means is changing the data value. So again, we're going to change the data value so the units are removed, but again, to what means? Why are we doing this? So the theme of statistics is dealing with, what's the theme of statistics? Variation. So that is the theme of stats, right? Variation is definitely the theme of stats. Now, the standard deviation is a measure of variation, it turns out. Okay, so what exactly is the standard deviation? So please memorize this fact. A z-score is the number of standard, I'm going to abbreviate this, deviations, standard deviations, a data value, well, I guess I had enough room, but I have to abbreviate. So a data value is away from the mean. That's what a z-score is. How many standard deviations is a data value away from the mean? Again, so notice again the theme here. We use a measure of variation and center together to keep in mind, keep that in mind as you look at this fact. So where have we seen this before? Remember when we did this, the upper fence? We looked at Q3 plus 1.5 and the IQR. So the IQR is a kind of measure of variation. Okay, and Q3, remember, if you recall, that was part of the center, one edge of the center of all the distributions. So again, keep that in mind as we continue to look at this. So what is the z-score formula? There's this formula attached to this. So the z-score formula is the following. This is your data value. I'm going to write two different formulas. Minus mean divided by the standard deviation. So there's the population mean and the population standard deviation. So from the data value, subtract the mean and divide by the standard deviation. Or if you're looking at data, then this would be, again, your data value minus the mean of the data over the standard deviation of your data. Okay, so what does this do? Well, if you take a difference, it will tell us how far apart these two numbers are, the data value and the mean. That's all it is. But when you divide by sigma, what you're asking is how many times does sigma go into that difference? So again, that's why this is how many, this z-score here, is how many standard deviations this number is away from this number. So we first take the difference, divide, and then that tells you how many standard deviations are in that difference. So fact about a z-score. A z-score of 0 indicates that data value is at the center. Okay, so for example, if you had a data value that is 4 minus, and the mean, the population mean or sample mean happened to be 4, and let's say that the standard deviation is a 3, well, 4 minus 4 is 0, divided by 3 is still going to be 0. So if you're right at the center, the z-score means that you're right at the center. That's all it means. Now, what happens if you're a positive? If you look at a positive z-score, it indicates that the data value is to the right, greater than the mean. And then we have that a negative z-score indicates that data value is below the mean. So negative z-scores are below the mean, positive z-scores are above the mean. 0 means you're right at the mean. So the larger the absolute value of the z-score is, the greater more extreme the theta value is. So keep that in mind. So again, look at this formula. If you have something like 10 minus 3, and then say the standard deviation is 2, 10 is definitely larger than the mean. So 10 minus 3 is 7 halves. So this would be 3.5, a z-score 3.5, which, notice, if the standard deviation is the measure of spread, this thing is pretty far away. And that's what we're going to come to find out, is that how to read this number. Let's look at the following. The mean of a distribution of population size, states or territories, is 5.93 million people rounded, with a standard deviation of 7.2 million people. Okay, so let's look at Oregon's population is 4.22 million people. How many standard deviations is Oregon away from the mean? All right, so let's take a look at this. Oregon is 4.22, so the question is how many standard deviations is Oregon away from the mean? So what this means is z-score, because that's the definition of a z-score, how many standard deviations. So the question might say calculate the z-score or calculate how many standard deviations, blah, 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 blah. Okay, so here we're going to go 4.22 minus a mean of 5.93, and I'm going to divide this by 7.21. So when I enter this, I'm going to enter it as one thing. If you're all kind of hesitant with fractions and things, doing order of operations, I would suggest you use Desmos. You can do the graphing calculator or the scientific calculator. I prefer the graphing calculator, but I'm going to do the scientific calculator. So I'm going to type all this in that we just did into this formula. So what I got is 4.22, but what I'm going to do is I'm going to enter this one item, 4.22 minus 5.93. And then what I'm going to do here is I'm going to hit the division key, the slash key for division in my keyboard, and I do that, it pops into a fraction. There's also buttons here you can make it to a fraction as well. See right here, you can make it to a fraction. But I'm trying to speed this up and then slowing myself down. So it's divided by 7.21, and then off to the side of the screen, let me see if I can bring it in. There we go. Negative 0.2371. So what does that tell me? I'm going to just round this. It's off screen now, but I'll write it down. So this is approximately negative 0.237. I'm going to go round it to 2. Notice it's negative, so I am below the mean. That's one thing it tells me. Another thing it tells me is that as far as a standard deviation, and it's pretty large here, standard deviation, I'm about a quarter of that standard deviation below the mean. So that's telling me I'm very close to the mean. Okay, so that's what it tells me. Here is 7.21. Here's 4, 6, 7 is right here. That's about the location of the mean. And where's Oregon? 4.22. It's somewhere there. So again, not too far away from the mean. That's what it's telling me. What about California? Has a population of 38.97 million rounded. How many standard deviations is California away from the mean? Again, I'm going to calculate a z-score because that's how many standard deviations is a z-score. So I'm going to come over here, 38.97. That's my data value minus my mean of 5.93, and I'm going to divide this by 7.21. All right, let's do this again. And notice if I want, I'm going to clear this so you can see this. I can click this little fraction button and immediately pops a fraction. So I'm going to enter that 39.83, I think it was, minus 5.91. Let me just take a look. 593, okay. 7.21. Yep, 38.97, 38.7. Okay, so I am 4.58 standard deviations away from the mean. 4.5825. Okay, 4.5825. I'm going to approximate that. 4.825. So I am 4 standard deviations away. So this is an average distance, but that tells me that I'm really far away. I'm really far away from the mean. And indeed, there's California. I mean, and there's my mean. So you can see, relatively speaking, this number is far away. How big is 4.825? Well, let me do the following. I'm going to grab the CDC guidelines for child measurements. And these charts come in different measurements or different ways of classifying, but the whole idea of this chart is, when your child is born, the first thing a doctor is, my child okay? Well, then you go through these growth charts, and for the how old the child is, then we're going to put up against known populations. But if you look at it, these charts, like there'll be z-scores, and they'll say, look, there's the weight, this is another weight, there's another weight, and now these are set differentiated by z-scores. So we had at a 0, which means your child, then that connect that number to a weight, and what that weight means is that your child is average. 0.5 is your half a standard deviation above average, 1 standard deviation above average, 1.5 standard deviation above average, 2 standard deviations above average, or -2 below average. Or, yes, like I say, the weight of the child is -2. But you'll notice that it doesn't go to 3, it doesn't go to 4. So this is kind of, as far as measurements of childs are concerned, being above 2, or say above 3, that would be very, very unusual, either above or below. Okay, so this California is way above. I mean, this is almost 5 standard deviations. So that's what this is saying. This thing is really far away, really far away. I also did another little search here, and I typed in 3 Sigma Club, and it came up with these things about athletes. There's also for businesses, also known for these 3 Sigma whatever. Why 3 Sigma? 3 Sigma athlete. So like the Spark Athletic NFL draft. So this is about some football player this week. This time has come for the 2021 NFL draft. This person's age 21. Looks like they got drafted into the Indianapolis Colts. Blah 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 blah. Great. Why do they call it 3 Sigma athlete? Because if you're 3 standard deviations away from the mean, that's considered extreme. So what they're trying to say, hey, this athlete is extreme. No, they're above average, way above average. That's what they're trying to say. Of course, it doesn't say 3 Sigma plus or 3 Sigma negative, because that would be, of course, way below average. But of course, it's an NFL draft, so I'm assuming this is plus, 3 Sigma plus. So notice Sigma. Sigma? What Sigma? Wait, what Sigma? Yeah, this Sigma. Right? So that's what a z-score is a sigma. So what they're quoting you is z-score. 3 Sigma athlete means the 3 is, oops, I can't do that. I can't write on it, but the 3 is a z-score. Okay, so now let's look at New York population with 19.57 million. Minus, again, my 5.93, divide that by 7.21, and let's see what we get here for this one. And the reason I'm doing this again, this time I'm just going to replace that value here. And I get that New York is 1.8921. Hey, remember the growth charts we just looked at? This is not quite 2, right? But it's getting close to 2. So again, what this is telling us, yeah, New York is pretty far out there. It's almost 2 standard deviations away. 2 of these. Not quite, so it's not too far away. So where is New York? That's New York. And this is California. Okay, so, but I notice again, this is not that far away. It's still far away, and that's considered, right? When you saw that growth chart, you notice it went to 2 and -2. So as soon as you get beyond that, that's when you start really getting to the far out. And this is pretty far out, but right at that edge. So notice we can use z-scores to determine how far a data value is with respect to the mean as a measure of center and standard deviation as a measure of variation or spread. Let's do this one more time. Let's go for Vermont. How many standard deviations is Vermont away? All right, Vermont. So this is in millions of people, by the way. So this is not millions. So if I move this to a million, remember, I got to divide this by a million. 1, 2, 3, 4, 5, 6. So I'm just going to approximate this 0.62. Something. I'm going to go 6.3. Just going to round this. So 0.63, a million, right? Because these are all in millions. So I divide this by a million, I get 0.63, 630,000. Approximately divide by 7.21. So notice this is going to come out negative. I'm going to just type in 0.63, hit return, and what do I get? Yep, that indeed is negative. And again, I'm going to round. It went away, and I'm going to remember from memory, but it was negative 0.73. Hey, notice that is within one standard deviation. Okay, so it's negative, is below mean, but still within one, so it's not that extreme. And where is Vermont? Oh, notice again, Vermont is, again, it's almost 0, so that's a 2, 1. There's Vermont. That could be one of these. These are part of the territories. Vermont's almost at the edge here. But that's how far away. So yes, it's not close, but not too far away. Certainly a lot closer than New York. As a matter of fact, there's a center. Where's one standard deviation? So one standard deviation is, well, it's 7. So, okay, I got 5. Is that the mean? No, I got that mixed up. The mean is 5.93. So this is 4, 6, so 5.93 is close right here. That's where the mean's located. So again, not too far away. New York, now put New York a little further away. So now, if that's the case, this is about 7. So I'm going to call this 6 right now to make it simple. 6 plus 3 is 13. That's 14. So one standard deviation is about right there. And if I go 7 on the other, one standard deviation is over there. So notice these numbers, the vast majority of all the data is within one standard deviation away from the mean. So that tells you something. Yeah, these values are not within 1. And of course, we saw that the standard deviation is not a resistant measure. So this value, the 7.21, is being enlarged because of California. New York here is also not as much, but California is certainly pulling things. And what is this state right here? This should be Texas. And what about this other state next to New York? That should be Florida. So we got 3 biggest states are California, Texas by far, then Florida and New York follow that. Before I leave that, let me make one more mention. Remember, we determined that California, Texas, Florida, and New York were all outliers under the 1.5 IQR rule. All right, so when we did the Q3 plus 1.5 IQR, we found, and that's calculated as the upper fence, we found all of these values to be outliers. So notice this is about 1.8921 standard deviations away. So yeah, we're at the region here where we start considering these as outliers. So we want to connect, between measurements. Okay, these were outliers under this rule. Clearly this thing is an outlier without even any need for calculation. This is California. But again, we're comparing 2 different measurements and they're both trying to tell you it's the same thing. Should we be considering these as outliers? The z-scores are going to be a little different beast to get a nice clean read from, but you start getting the sense of it by looking at this. So just to understand what a z-score is, I'm going to do the following. The median of the distribution of population size of territories is 3.675 and the IQR is 5.67 million. So again, the median is right here. And then that IQR is that distance between Q3 and Q1. And notice we could ask this following question: how many IQRs is New York away from the median? So let's just try this again, but this time with IQRs. Now, nobody does this, but you could. And just so we can get an idea, you would take your measurement, which is 19.7. The question is, how many IQRs is this away from your median? The median being this number. And you divide this by 5.67. And let's see what we get. I just stopped the video and typed it in, and there you go. It's about 2.7874, 7874. Okay. And that's how many IQRs. Okay, so you can see the formula, how it works. This is how many IQRs. But nobody uses this, but we do use the z-score and the standard deviation. That is definitely used, but you could. And now we get an idea that New York is 2.78 IQRs away. Before, New York was 1.89 standard deviations away. But the IQR definitely does not involve all these data values. Remember, the IQR, all it cares about is the middle 50%. So we're comparing the middle 50% and using that as our measure of spread. And here we're taking into account all the data value for the z-score is all the data values, and we're using that as a measure of spread. Okay. Notice again how kind of, unless I did something wrong, New York is, quite, as far as an IQR is actually further away than the standard deviation. Isn't that interesting? So again, this is not a statistic that's ever found in books or is quoted in a publication. I've seen it, but it could be. So I've never seen this thing. But again, just to compare and contrast between these two. Right, one last thing. Using z-score to compare relative position. Okay, the histograms show the distribution of bone density in rats. Now, some of the rats were exposed to a set of exercises, jumping, and one set was not. The box plots show the data separated by the group that were exposed to. Again, there was a low jump, high jump, and a control, no jump rat. And then what's being measured is the bone density. With data separated by groups, what information does the stacked box plot provide? Well, here's all the data together. But now, when we look at the box plots separated by control, low jump, and high jump, you can start seeing detail. I can now see different groups vary and how much overlap there are. Okay, so that is kind of a nice feature of the separating. Now we can tell, for example, that the as far as is concerned, the bone density of the rats with a high jump group are much greater than the control group. Notice that here is the median for the control group, and if I come down, so notice this one instance. All the rats in the high jump group had a bone density above the median of the control group. That's considered, right? So the question is, does exercise increase? How does it affect the bone density? And in this case, it definitely affected. Notice that. And so there's variation within the high jump group, just as there's variation within the control group. And you'll notice that there's one rat that was in the control group, and their bone density was pretty high, considering they didn't do anything. And the low jump group, they did pretty well. But there's a lot more variation. One thing to note is they suffered a little, not as good, but not too bad. So nearly, it's kind of hard to say, right? So this is 75%, the first quartile. Here's the first quartile. And so there's more, I guess there's more variability in the low jump group. Yeah. And again, it would take us a while to kind of diagnose this, but the idea is that we start comparing items between the two. Certainly, notice that middle, that's the third quartile, there's a lot more variability in the low jump group. That's interesting. Anyway, one thing also did is the bone density in the lowest, it was not as bad compared to the low jump group. All right. Now let's get to this part here. Bob the Rat was part of the low jump group. Okay, Bob the Rat. While Tony the Rat was part of the high jump group. So low jump and high jump. Both the rat, Bob the Rat had a bone density of 5.93. Tony the Rat had a bone density of 6.5. Relatively speaking, within the respective groups, which rat had the lower bone density relative to the respective group? So what that means, I need to find the z-score. The z-score will allow us to see the differences. So I'm going to speed this up. So the z-score here, notice I put the z-score, and because it's going to be for Bob, Bob was the rat in the low jump group. So there's my low jump group. So I'm going to use these values for Bob because he was in the low jump group. And I get a bone density of negative 0.101. So now I'm going to go Z for Tony, the high jump rat. And if I do that, what do I get? Well, just 615 was Tony. Yep, 615 milligrams. And I put a 593. I'm not sure why I put a decimal. I didn't calculate with a decimal, by the way. That's incorrect. I'm not sure why I did that. And, nope, 638. I'm going to fix that. And here we go. And I get here negative 1.43. Okay, so remember what a z-score is. Both were negative. Both Tony was below average in this group, and Bob was also below average. But it turns out that Tony in the high jump group was way more below average than Bob in his respective group. So relatively speaking, which rat had the lower bone density? Well, again, notice Bob had a bone density. Let me get rid of that point here. It's bothering me. There we go. 593 milligrams. So in absolute value, Bob definitely has a lower bone density than Tony. But with respect to their groups, Tony has a lower bone density. So Bob is the winner. Relatively speaking, which rat had the lower bone density? Tony. Tony had the So one thing the z-score allows us to do is we can sort of compare these numbers within their each group. Okay, obviously, again, Tony has a higher bone density than Bob, but relative to their respective group, Tony now is lower because Tony is further below average. So here's -1, Bob is right here, and here's -2, and Tony is further away from the average, 1.5. So there is Tony right there. There's Bob. So Tony has a lower relative bone density. When we look back at the growth chart, notice they separate by gender, and then they have the two different growth charts, one for females, one for males. Because again, there is just different physiology, and you want to compare apples to apples. But then you can always come back, turn into a z-score, and compare. This person was on average taller for the respective group. For example, my niece, but 13, was close to 6 feet tall. But for a young woman to be nearly 6 feet tall at 13, when she walked, she looked like a giant. Why? Because relative to where she should have been, or everybody else was at her age, she was just abnormally tall. She wasn't, there's boys that were bigger than her, but she just stood out. And even with the boys, she just stood out because, relatively speaking, she was a giant.